So we're gonna briefly talk about what chemistry is, scientific notation, and do some conversions, basically all kinds of cool stuff. So the definition of chemistry here: composition, structure, properties, and reactions for the most part. Of course, properties, reaction, and composition. Structure is also important. Okay? So these are the terms you should be familiar with. So composition. You can study minerals, what they are made of. That would be analytical chemistry. Structure, how atoms or molecules organized within a substance. That would be more like crystallochemistry. Okay. Properties, characteristics. So we are going to talk about some physical characteristics, such as density, but in chemistry, of course, we are looking for the most part at chemical characteristics. In other words, how does it react with other substances? Okay? Questions? Good? Okay, let's move on. So, the word that we use for everything that surrounds us is matter. As we will see soon, matter is anything that occupies space and has mass. So, here's my question for you. Well, obviously, antacid tablets matter, water is matter, but this, whatever surrounds us, that room, that what fills that room, that emptiness, does it matter? Yeah, it is. It's air. It's matter. It occupies volume, occupies space, and it does have mass. Okay? Another question, just out of curiosity. What about light? Does it matter? No, it's not. Light is not. Light is a very tricky substance. Waves aren't matter. Field, like electromagnetic field, isn't matter. Light is waves. Waves, electromagnetic radiation. It is not matter. It is energy, though. So, concept when we say the word chemicals, okay? One of the key features of a chemical is this: they have same composition and the properties no matter where you find them. You can go to a grocery store and buy and buy water. Okay, fine, water. And the composition of water is 2 hydrogen and oxygen in each molecule. Doesn't matter where you buy it or where you get it. If it's water, it has the same composition. Okay? You can get sand, and that's going to be silicon dioxide, whether it's on Lake Erie or in Florida. Okay, chemical composition is the same. Things that we use in our daily lives are usually combinations of chemicals. This bottle is a combination of chemicals. Stables are the combinations of chemicals. Okay? So, what contains chemicals here? Can be more than one. Huh? Can. Okay. All 3 except sunlight. Exactly. Now, another concept that we're going to review today is the scientific method. And I want to make a small digression. I hope I can keep it small. It is not the only way to interact and understand the world. Okay? You can think about events in the world and phenomena in the world as being magical, or have religious explanations, or other rational explanations. Scientific method, it's a tool that operates to provide rational explanations to natural phenomena and find the laws that govern natural phenomena that can be proved, that have predictive power. So main steps that you should know, we start with an observation. Remember on Monday you looked at this transparent pocket of chips, okay? Based on that observation, you formulate the hypothesis. Sometimes people formulate the research question before. Okay, so you would say, okay, the question was how many chips are in your bag? And based on that question, you formulate hypothesis. Blah, 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 so many chips. Then you do experiments. Okay? And experiments may prove or disprove your hypothesis. Which type do you think is more valuable? Experiments that can verify your hypothesis, or experiments that can potentially falsify it? So, of course, this is the fundamental principle of scientific inquiry. You always want to prove yourself or other people wrong. One of my favorite stories is Michelson-Morley experiment. If you happen to be in Cleveland, there's a building, Case Western, where this experiment was done. These two fellas tried to disprove Einstein's special relativity theory. They made a really complicated contraption, did a bunch of experiments, couldn't. They did specifically to disprove, not to confirm. And the results that they were expecting were not the results that they got. Like, okay, cool. Got Nobel Prize later. So, based on the results, you formulate the conclusion. Okay? And then, if your hypothesis stands, what do you do? Do you celebrate, go for a drink, and that's it? What do you do? What do you do? I just told you pretty much. You design another experiment to try to disprove it again. Multiple experiments that validate your hypothesis make it a theory. Okay, good? There's one thing that's missing on that slide. So let's say I'm a scientist, okay? I have a hypothesis, I did experiments, look at the data, all points that, my hypothesis is correct. I keep doing this. How do I know? What am I missing in my process? So I do all these steps and yet I'm missing something. When you get the results, what do you need to do with them? Just for yourself? You got to publish them, right? So other people would validate your interpretation of the results, your hypothesis, whether your experiments were suitable. This is called peer review. Bingo. And this is I have done 15 years of scientific research. If you want to learn about scientific results, data, you've got to look at peer-reviewed research or peer-reviewed reviews of that research. But you can't go to, New York Times or Washington Post or New York Post or whatever, or Natural Medicine by Haley and take it as a source, as a reliable source. Am I making sense? Seriously, it's one of the biggest problems in our country. Now, when the hypothesis gets tested over and over again, and all experimental data show that it's correct, becomes a theory. Okay? What is the difference between the theory and the law? Okay, one by one. No. That theory is a thoroughly tested and confirmed hypothesis. But why do we, what is the goal of a theory? Absolutely not, no. Why do we formulate a theory? Like, for instance, we have a theory of relativity, or theory of gravity. What is the difference between the theory of gravity and the law of gravity? Law is, but
the law is what you're seeing, and the theory is describes how it happens.
Exactly. Law is like, if you're going to take an object, stick it out of the window and release it, it's going to fall on the ground. Try to do it different. You can try it yourself. Okay? This is the law. Newton's theory explains how this law works, what mathematical apparatus can be derived from that. That's a theory. Okay? Does that make sense? Good? Okay. Now we're going to get very, very technical. Scientific notation. You still see it fine? Let me check if it's okay. Perfect. Okay. So just a reminder, I guess all of you encountered that. Okay. So scientific notation, we convert either very large or very small numbers in the more readable format. Right? So how do you do that logistically? Remember that if you have a number like this 2400 that you have right here, okay, we don't put decimal point to the right, but it's still there. So if we want to make it shorter, you take the decimal point and move it so it separates. It creates the number in the beginning like this. So the first number before the decimal point in scientific notation should be 1 or more, but less than 10. So 1 through 9. Okay? And then you write whatever numbers are left and multiply it by the 10 in the power of how many steps to the left you took. We're gonna do some practice right now. And if you do the same operation with a very small number, you move decimal point using the same guidance in terms of the appearance, but to the right. And you multiplied the resulted number by 10 in the power of negative steps that you took to get to that position of a decimal point. So here's a couple of examples. So first of all, speed of light. It's kind of approximately. $300 million meters per second. Okay? So Scientific notation. We take this decimal point. 1, 2, 3, 4, 5, 6, 7, 8. Why I shouldn't do step number 9. One more to the left. Because then it would be 0, right? So 3 multiplied by 10 and the number of steps that I took in the power of 8 meters per second. Fair? Questions about that? Now something small. I think it's sodium emission spectrum. Just one of the lines. It's 0, 0, 0, 0, 0, 0, 0, 585 meter. Okay? Make sense? So, what do? 1, 2, 3, 4, 5, 6, 7. Not 8, just 7. Okay, good. So what we get out of this is 5.85. How many steps? 7, but to the right, so it's got to be negative. Okay? Awesome. So, don't worry. This is all going to be saved as PDF with all my annotations and uploaded on the Blackboard. I know. Do you want me to read the numbers and letters to you? I mean, it's kind of fun to look at it. It's just a conversion part, okay? Like diameter of the Earth, 12.8. Well, 12,800 kilometers or 12,800,000 meters, or you can write it as 1.28 meters, 1.28 in the power of 27, 10 in the power of 7 meters. I'm becoming dyslexic today. I find it embarrassing to explain to a bunch of adults how to use a scientific calculator. Okay? You can figure it out. The only thing that I want to highlight, they don't write 10 in the power of whatever number it is. It's this letter E. It basically means 10 in the power of. Okay? Yes, you are in the chemistry class. I know that you all can read scientific notations on calculators. You seem like a reasonable bunch. Whatever your calculator is, use the second or third button. I don't know. It really is embarrassing. But at least it was short. Well, shameful. Let's write 64,000 in scientific notation. How many steps should I take? Which direction? Wait, what? To the left. Okay, yes. To the left, yes. To the left. So we go 1, 2, 3, 4. And get 6.4. 10 in the power of 4, right? In case of example B, how many steps should I take? Which direction? Right. 10 in it, yes, 2.1. 10 in a negative 7. Good? Perfect.